All right. A couple of questions there were, um, are the tests due today? As soon as you can get them to me, okay? The most important, well, I don't say most important thing. One very important thing is to get your research paper in by Thursday, okay? Please get it in by Thursday, because after Thursday you start losing points, okay? In fact, the last bonus point was yesterday, okay? Because that was November. If you get it in this week, you just get your score, okay? If you get it in after Thursday, you start losing points. So please get your research papers in for those who haven't. Several of you have. This has been a pretty good class about getting that kind of stuff done. Now, your back tests, get those in just as soon as you can. Today, tomorrow, Thursday, okay? Try to get them in as soon as you can. I'm not going to have a lot of time this week to grade, but any time that I do have, I'd like to have the opportunity to get as many graded as possible. Then on Thursday after class, at the end of class, I will be giving you your Chapter 2 test, which is going to be very short. Oh, here comes, I'm guessing it's Shamari. But I'm not absolutely sure until I found out. Shamari, is that you who just came in, PC?
Yes.
Okay, good. I thought it was. But anyone else could be using that tag too, so just wanted to make sure. All right, we broke double digits now. 3, 6, 9, 10. Yep, we got 10 students here. Way to go. I hope more will be coming. So try to get your research papers in by Thursday, and sooner is better, okay? And all your back tests in also by Thursday if possible. There's no losing points on the test, but I don't want you out there, because you see, Thursday I will be giving you a very short Chapter 2 test, but then also your final exam, and that's going to be very short. So you've got a lot coming on Thursday. I don't want you having any of the back tests still on top of you. That's a bit much. So that will be coming up Thursday. All right. I had planned to go over how we're going to end the course, and we've just about done it. We're at the end of 2.4 now. Hopefully we'll move right into 2.5 and get a lot done of that today, and then hopefully get a little of 2.6 done on Thursday. Any questions? How we're going to wrap this up? Okay. Then, if not, let's get the share screen started. And here's 2.4. We'll get that started. Oh, here comes Ashford. Let me get Ashford in. Okay. Now we got enough for a football team. 11 students here. Okay. Of course, you'll have to go both ways, but y'all can handle that, can't you? Okay. Let's get the going from current slide. And let me get these things moved around. I don't know why they put their taskbars not quite in the middle of the page, but right in the way. And then I'm also going to bring up the whiteboard, because I think we'll be doing this one. And again, that one's not in the middle, but it's in the white space. I like to move it out of the white space so I get as much room as possible to write. Okay. All right. And here comes Ivan. Let me get Ivan in. All right. We are filling up, not filling up, but we're getting fuller all the time. Okay, Ivan's right below the blue line. There we go. All right, now, top part of the alphabet is doing pretty well. Bottom part's doing pretty well, and the middle part's doing pretty well, but we're in between. There's some pretty big gaps there, so hopefully more will be coming in. All right, Any other questions, issues, problems, concerns before we get started on today's class? Okay. I hear none. And we're starting in example 5. And I'm trying to do these real quickly because you're not really responsible for these, but you may run into them sometime in the future, and I want you to be prepared for that. Okay? This is Chapter 2, Polynomial and Rational Functions. Section 2.4 is complex numbers, which was not in your course description. However, it is something you'll bump into, and so I want you to be able to handle that when you can, as you need to. So let's do example 5. It's not on the power. Oh, here comes Briantra. Let me get her here. Hold on just a minute. I'm wired in place here, and it's hard for me to get over. Briantra is here. She's the middle, and there we go. Middle alphabet just got a bit stronger there. If we were playing, what was that old game, War or something like that, where you try to pile up positions in different places. Okay. Here's example 5. 3 parts to it. If I can get my pen to show, there it is. Okay. The square root of -3 times the square root of -12. Now, there's 2 ways that you can do this problem. Okay? Now, it may be your first. Do any of you have an inclination of how you would do the problem? Okay. Ashford, Ashford, I'm not sure, but I believe you got your microphone on with some noise in the background. Okay, someone's on a phone call and you got your microphone on. Is it you, Ashford? Okay, good, thank you. All right, now, if your first inclination was to deal with each one of these, that would be fine. This would be I'll write it out in gory detail. The square root of -1 times the square root of 3. And this would be, well, here comes Tommy. Let me get Tommy in the room. Okay, so here we go through this, moving around again. Tommy Easley is here. Okay, got it. That strengthens the top of the alphabet's position. Okay, now something else popped up here. Let me make sure there's no one else in the waiting room that I didn't see. Okay, it looks like we got everybody. Should have 14 students now. Let me just check that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Got it. Okay. So you could do it this way and then break that we're doing, Tommy and those who just may have come in. Chapter 2, Polynomial and Rational Functions, Section 2.4, Complex Numbers, page 149, example 5. Okay? You could break this square root of -12 into the square root of -1 times the square root, the square root of 4 times the square root of 3. Okay? Now, you don't have to do this, but this is one way you could do the problem. Well, the square root of -1 times the square root of -1 gives you -1. Square root of 3 times the square root of 3 gives you 3. Square root of 4 is 2. So this would give you -6. Okay? Now that's, even though it's long, messy, a little awkward, that's the way to do the problem. If your temptation was to use the rules for regular radicals, you would have said this is the square root of -3 times -12 is positive 36, and the square root of 36 is 6. Resist that temptation, okay? You have to deal with the i's in there, okay? Because multiplying these two together wiped out the square root of -1 times the square root of -1, which gave you a -1. So that's the thing to watch for. Always pull out the I first, the square root of -1. The other way you could have said this is I times I, and I squared is -1. All right, let's do the B problem. Are there any questions on that? All right, the B problem is the square root of -48 minus the square root of -27. Okay, now what would that be? Well, again, I would suggest pulling out the square root of -1. That's going to be I. Then see if you have any perfect squares in there. And you can do it however you want to. We don't count 1. That is a perfect square, but that's in every factor. Okay. The square 2 is a perfect. Okay. 4 is a square. 2 is the square root of 4, and you do have a square root of 4 in there, so let's factor out a square root of 4, and that would leave you a 12. Well, you have another 4 in there, and that would leave the square root of 3. Okay, minus, now the square root of -27, first pull out the square root of -1. That's a pretty ugly -1. And then you have 27, and certainly 4 is not in there, but 3 squared is 9. 9 is in there, so that's square root of 3 squared. That's 9. Well, let's just write it square root of 9. Okay, and then what you have left over is the square root of 3. Okay, now this is an I. This is a 2 times 2 is 4 root 3. Okay, minus this is an I, and this is a 3 root 3. So written a little bit neater. Now this is how I write it. The book writes it the other way, but this is how I do. 4I root 3 minus 3I root 3 would be I times root 3. Now the book writes it root 3I, I'm sure. Okay? The reason I don't is that sometimes sloppiness in writing, you might think that I is under the radical. It's not. This. Okay, my internet connection is unstable, so I'm going to quit talking math and just, okay, did I break up some there? Was anyone listening? Okay. Well. A little. Okay. Well, I got a message that my internet connection was unstable. I've got 4 bars, so I don't know why it would have been unstable, but anyway, y'all are welcome to come to any of my bars. No, that was beside the point. All right. Let's do the C part. I'm trying to do these quickly, but I'm talking too much. I think I'm going to clear my screen. Does anyone need this up a little bit longer to get? Anybody? Okay, I'm going to clear all the drawings in. Okay, the C part. Here's what we have. Open parentheses, -1 plus the square root of -3, and we're going to square that. Okay? Now, I would suggest go on and write this as -1 plus, and break this down into the square root of -1 times the square root of 3. and we're going to square that. Well, this would be -1 plus, and I like to write it I root 3. And we're going to square that. Okay, so how do we square this? We square the first term. Oh, here comes Rosa. Let me get Rosa in here. And here I have to go again with my decoupling here from all the wires that I have. Rosa's here. The top part of the alphabet is really taking over now. They have perfect attendance down through Tommy. Now I can't remember for sure, but I think I saw that Janae had to withdraw. I know she had been missing classes she never missed before, but she missed one week and 2 the next week, so she may be withdrawn. But the others we don't have. Then we got 4 in a row in the middle of the alphabet and 3 in a row at the end of the alphabet. So keep them coming, folks. Okay. Now, goodness, I just forgot who I put in. Oh, Rosa. Rosa, we're in Chapter 2, Polynomial and Rational Functions, Section 2.4, Complex Numbers. We're doing Example 5. We're on C right now. And here comes Ladarius. So here we go again. Hold on. I've got to decouple from all my wiring here. Ladarius is here. That really boosts the okay. The strange thing is I already had Ladarius here. I put Anaya on the wrong line, and I had moved everybody else up. So now I've got all of you where you needed to be. So the bottom part of the alphabet is caught up with the middle part, and we'll see who's going to win. Okay, we're just pretending. Ladarius, we're in Chapter 2, Polynomial and Rational Functions, Section 2.4, Complex Numbers, and Example 5C is what we're working on now. And we've gotten it down to this stage. Now we're squaring a binomial. Okay, well, what we have here, -1 squared is 1. Okay, then it's twice the product of the 2. That would be a -2 I root 3. Now I write this differently from what the book does, but that's twice the product of the 2 terms, and then it's normally, I'll go on and do it, plus the last term squared. Well, the last term squared is I squared times root 3 squared. Okay, did someone have something you're trying to say? Okay, now I'll put a parenthesis in front, so I'll put 1 at the end. This will be 1 minus 2 I root 3, and the book doesn't like me to write it that way, but they can't control me. The I squared is -1. Okay, root 3 squared is 3, so this becomes -3. Okay, then when you combine those two real parts, that gives you a -2 minus 2 I root 3. Now you could, if you wanted to, factor out the -2 and have it as that time 1 minus I root 3. There's no reason to do that at the end, but you could. And they leave it in this form here. -2 minus, now they always put the I at the end of the number because that's standard form. But to me, to put the I over here after the radical introduces the possibility you might think it's inside the radical when it's not. Okay, so that's why I put it in front of the radical. You know it's not inside the radical there. Okay, that's example 5. Any questions about those? Okay, there is a checkpoint, like there's always a checkpoint after every example. So I think example 6 is on the slide set. So let's go back to the PowerPoint and go to here. Yep, there's example 6. Now, I don't know why all this mess is in the way. There we go. Got rid of most of it. So here's example 6. I don't need the book at my lap anymore, so I'll get rid of that heavy thing. And it says solve this equation. Okay. Well, that's a quadratic equation in standard form. Okay. Now that's not a quadratic function in standard form. This is a quadratic equation in standard form. It has a left-hand side equal to a right-hand side. Quadratic function is f of x equals something another. Okay. And it could be that same 3x squared blah blah blah. Okay. So what would we try? Well, if we could, we'd want to factor it. Okay. Just in the interest of saving time, you cannot factor this polynomial. Okay. There is no way in the world that will ever factor. Okay. So the next best thing is quadratic formula. A quadratic formula tells you that x is equal to, now identify your coefficients. A is equal to 3, B is equal to -2, and C is equal to 5. Okay, that's your A, your B, and your C. So x is equal to minus B plus or minus the square root of B squared minus 4AC. And all that is divided by 2a. That's your standard quadratic formula for any quadratic equation in standard form, written in the squared term, the linear term, the constant term equals 0. Okay, so let's start our plugging and chugging. Our b was -2, so minus b will be +2, plus or minus the square root of b squared, -2 squared is 4. Okay, now what I do is write down the rest of them. -4 times a, which is 3, times c, which is 5. Okay, over 2 times 3 is 6. I'll just go on and do that one. Okay, now the reason I strung this one out, 2 plus or minus the square root of 4. Now, at this stage, count your negative signs. The -4 is always a -4. Okay, so that's always one. These two are both positive. You only got one negative sign. That means this is going to be minus. And then what is it minus? 4 times 5 is 20, times 3 is 60. Okay, over 6. Okay, and that would be 2 plus or minus the square root of -56 over 6. All right, now at this stage I'll write it as 2 plus or minus, now let's pull out the square root of -1. You don't have to do this once you get it that you really understand it, but I like to show it this way. Now, are there any other perfect squares hiding in 56? Well, 56 is 8 times 7, isn't it? I believe it is. And 8 certainly does have a perfect square in it, 4. So let's factor out a 4, the square root of 4. And 4 will go into 56 I think it's 14 times. So the square root of 14 does not have any perfect squares in it. Okay, and all this is over 6. Okay, so this becomes 2 plus or minus, I'm doing this in gory detail now. I'm going to bring the square root of 4 in front and make that a 2. And then I'm going to put my I, because I like to put the I outside. Now, did someone else just try to come in the class, or did I kind of bump this. Let me just see. I should have 15 students here. Let's see what I've got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I have 16 students here. We must have lost somebody. That's why it bopped up there. Okay. Sorry about that. Interrupting the flow of the class. Okay. So hopefully that student will be trying to get back in shortly. And I can't find my pen. I had it. There it is. Okay. So here's the 2, there's the I, and here's the square root of 14. Now the book doesn't do it this way. They always put the I at the end. I find that too big of a problem waiting to snatch you into its grips. Okay, now there's a 2 in both terms here, so these become 1s, and there's a 2 down here, and that becomes 3. So in standard form, this x would be 1. I'm going to break it into 2 parts now, plus it's 1/3 plus I root 14. The book will always do it root 14i. Root 14i over 3. And the second solution is its conjugate, which is 1/3 minus. Now if you write it this way, I'm going to show you another way to write it. The square root of 14, because this is a fractional form, over 3, that's pretty clearly the I is outside the radical there. So that may be a better way to write the first one. You know, write the square root of 14 over 3i. Let's see what they got in the book. Oh wait, they're going to work this out for us, and that's exactly what they get, only they leave it in the plus or minus form, so I don't know why. Okay, so anyway, let's clear my scratch out of the way. Any questions before I clear it? Any? Okay, let's erase all the ink and see how they proceed. Okay, there's your quadratic formula, though they didn't write it down for you. They just plugged in the numbers, same numbers we used, and that's the same thing we got, 2 plus or minus the square root of negative 56 over 6, which is, and without showing you how they got it, they put 2 plus or minus 2 root 14i. See, they like to put it after the radical, which in print, in typeset, yeah, you can tell it's outside. But you know, if you looked at it closely, you might think it's inside. Over 6, and here you can divide out this 2 into 6 and 2 into those 2 2's, and that gives you 1/3. 2 over 6 is 1/3, plus or minus another 1/3, so root 14 over 3 times I. Now in this case, it's pretty obvious that I is not under the radical. So that probably is a reasonable way to write the answer. Now if you're doing this for WebAssign, they're going to want the answer in only one form. Okay, and they'll say it's wrong if it's not. Okay, but you can write it in several forms, and you can get by with that on the tests and things, as long as they're the right forms, the right numbers. So any questions? All right, that does finish. Yes. Okay. But it was after class. Right, and she told me that earlier, so thank you. Yeah, and this is Shay talking now, right? Yes, sir. Okay, good. Yeah. Okay, yeah, I know it. And just remind me right at the end of class. Okay. All right. As in all examples, there is a checkpoint, so please do the checkpoint. Well, these with the I's in them, you don't have to worry with those too much. Let's do real quickly the vocabulary on page 150. Okay. A blank number has the form of a plus bi, where a is not equal to 0 and b is equal to 0. So that's a very special form. I'm going to write it down here. Whoops, I'm on the wrong pad. Okay, I'll write it here. A plus bi, where a is not equal to 0, but b is equal to 0. Oh, here comes, this must have been what the thing was. Shamari had to get out and she came back. So now we're back up to 16 students, I hope. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, we're back to our full complement again. So what kind of a number is a plus bi that has this form, that form, but a is not equal to 0, b is equal to 0? What kind of number is that? If that b is 0, that means there's no imaginary part to it. And if a is not 0, that is a real number. Okay? Now, number 2, an, starting with an, not a, number, blank number, has the form of a plus bi, but in this case, a is not 0. I'm trying to, and b is not 0. Same form. What kind of number is that? I'll tell you what, when I'm doing this, I would call that a complex number with an imaginary component. What the book calls it is an imaginary number, and that's why they have the an in front. Either one of those is fine. It really doesn't matter what you call them as long as you use them right. Okay? But anyway, now, the third one, a blank blank number, has the form a plus bi, same form, where a is equal to 0, but b is not equal to 0. What would you call that? A blank blank, where a is equal to 0, if I could get my pen to show up, that is 0, but b is not 0. A blank blank number. That is what I called, the book calls, everybody calls, a pure imaginary number. There is no real component to it that doesn't have an I with it. That's called a pure imaginary number. So when the b is 0, that's just a real number. When neither are 0, they call those imaginary numbers, which are correct. But I always think of the imaginary number as I. It's called the imaginary unit in this case. So I call it a complex number with an imaginary part to it. And somebody had to leave. I'm guessing it's Shamari again, but we'll see. And then if the a is 0 and the b is not, then that's a pure imaginary number because it has no real part to it. Okay? Number 4. The imaginary unit I is defined as, you tell me, how is I defined? If I could get my pen, here it is. I is equal to, what's the rule for what is I? I've done it in several of the examples here. The square root of minus 1. That's what it is. And what is I squared then? That would be, how in the world did that happen? Okay, here's Diana. Let me get Diana in, and that means I have to untangle myself here. And here is Diana. All right. Getting up a pretty good number here today. I just had written something wrong, and this is so aggravating. There. I don't know where the 2 came from. I was starting to say the square root of -1, and I wrote 2 instead of 1. I have no clue how that slipped in there. I squared is -1. Okay? And let's see, that's number 4. Number 5, when a is a positive real number, the blank blank root of -a is defined as negative. Okay, I don't know what happened. I think someone else must have had to leave. Let me see if anyone's waiting. Sorry about this. These things keep popping up, and I want to make sure I don't have anyone stuck in the waiting room. Okay. Number 5. When a is a positive real number, the blank blank root of -a is defined as the square root of -a as the square root of a times I, or I times root a. And I think that's called the principal imaginary root. Let's just see. They call it the principal square root. Okay. That's what you would call it anyway. Okay. So nothing new there. Number 6. The numbers a plus bi and a minus bi are called blank blank, and their product is a squared plus b squared. What are these two called? Blank blank. Well, anytime you have a binomial, first term's the same, second term's the same, except for the sign, those are conjugates of each other. And since these are imaginary numbers in here, complex numbers here, they're called the complex conjugates. So that's the blank blank. Okay, now these homework exercises, folks, you don't really have to do any of them. Okay? Because these all have the I's in them, but I did want you to be exposed to this information. There are a few of the problems there that do not have I's in them. So, for instance, number 17, there aren't many. 45. I don't know what you do with them, but you can play around with them if you want to. Just about every one of them deals with. Okay, now I haven't worked out all these. I bet you their answers are all have I's in them, but if any of 67 to 75 do not have I's in them, then you can do those. 87, especially if any of you are going into electrical or electronic thing, that may be an interesting problem for you, but it does have I's in them, so I'm not going to require you to do that. 89 you might be able to answer without doing too much, and that's it. Let's move on to 2.5. Any questions on 2.4? I probably spent too much time on it. So let's move on to 2.5. And we'll go from current slide. All right. We're still in Chapter 2, Polynomial and Rational Functions. Now we're in the last part of polynomial functions, and what we're looking for here in 2.5 is zeros of polynomial functions. Now, if you remember what the zero of a function is, it's where the function is equal to 0. In other words, the y is equal to 0, because the function f of x is always y. That's where you have your x-intercepts, where y is equal to 0, where it crosses the horizontal axis. Okay? Now there's a a whole bunch of objectives here. Use the fundamental theorem of algebra to determine the number of zeros in polynomial functions. That turns out being a pretty easy thing to do, believe it or not. Number 2, finding the rational zeros of polynomial function. That's going to be sort of fun. It's a new procedure, so we'll be doing that. Find the conjugate pairs of complex zeros. We're kind of like skip over that because we're really not doing the complex, but I'll show you what they look like. Find the zeros of polynomials by factoring. Yes, that's a biggie. And use Descartes' rule of signs and the upper and lower bounds rules to find zeros of polynomials. That's a pretty important tool, two or three important tools to have in your belt, and find the zeros of polynomials in some real life application. So let's start with the fundamental theorem of algebra. In the complex number system, every nth degree polynomial, here it is, every nth degree polynomial has precisely n zeros. Now that sounds like a contradiction, because back before we said every nth degree polynomial has up to n real zeros. Oh, we stuck that real in there, didn't we? In the complex number system, every nth degree polynomial has precisely n zeros. That allows for complex zeros. If there were real zeros, it has up to n zeros. If you're including complex numbers, it has precisely n zeros. That important result is derived from the fundamental theorem of algebra. Now they say here, first proved by the German mathematician Carl Friedrich Gauss. Now if you haven't gotten a paper topic yet, he's an excellent one. Okay? But I'm going to throw another name at you. The French believe that their mathematician, not the German, I can't remember his first name, but D'Alembert was his last name, actually discovered this about the same time and independent from Gauss, sort of like Newton and Leibniz in calculus. They did it somewhat independently of each other. So the French will call the fundamental theorem of algebra D'Alembert's theorem. Okay, there's some dispute here, but most people agree with Gauss. The fundamental theorem of algebra. Now this doesn't sound at all or precisely this, but here's the fundamental theorem of algebra. If f of x is a polynomial of degree n greater than 0, in other words, a linear function or up, okay, then f has at least one 0 in the complex number system. Wait a minute, that doesn't sound anything like this. This says it has precisely n zeros for whatever n is. This one says it has at least one. This was the first theorem that you had to do first, and then you built on this to get up to that one. Okay? Using the fundamental theorem of algebra and the equivalence of zeros and factors, and you know what that means. If x equal a is a 0, then x minus a is a factor. Okay, that's what that means. You obtain the linear factorization theorem, which states this. If f is a polynomial of degree n greater than 0, then f has precisely n linear factors. Okay, where f of x would then be some leading coefficient a sub n. Okay, and then x minus c1 times x minus c2 times x minus c3, all the way down to x minus c sub n. N linear factors, but these c's in here are now complex numbers. Now remember, all real numbers are complex numbers, so they could be real numbers, or they could not be real numbers. They could have imaginary components in them. So these are either real or imaginary numbers, but they are all complex numbers. And you have precisely n linear factors, and therefore x equals c1 would be a 0, x equals C2 would be a 0, x equals C3, all the way up to x equals Cn. So you would have precisely n complex zeros. Note that the fundamental theorem of algebra and the linear factorization theorem tell you only that the zeros or the factors of the polynomials exist, but they don't tell you how to find them. That's the problem. Such theorems are called existence theorems. They are necessary, but they're not always all that useful. Okay, so what we're going to do from now on is try to find these zeros. We know they exist. We've got to find them now. Okay, so here's a first degree polynomial function. F of x is equal to x minus 2. Okay, because the degree is 1, we know it has exactly 1 0. Set that equal to 0 and you get x equal 2. Add 2 to both sides. X minus 2 equals 0. Add 2 to both sides. You get x equal 2. Wow, what an example. And they did all the work for you. Why didn't they have you find the 0? That would have made more sense. Okay, they'll probably do the same thing on this one. Counting multiplicity, the second degree polynomial function, this one. Now they didn't give you the answer here. This is a little more complicated, so they make you do the answer. Okay, well, this will factor. Okay, and because the first term is a perfect square, the last term's a perfect square, the middle term is exactly twice the product of those two square roots, this would factor as x minus 3 times x minus 3. Okay, how you do this? The only possible factorization for x is x times x. Because this sign here is positive, these two signs have to be the same. Because the middle sign is negative, these have to be negative. And then one possible factorization of 9 is 3 times 3. Let's see if it works. X times x is x squared. Minus 3x is minus 6x plus 9. Yes, that works. Okay. Now, counting multiplicity, this has 2 zeros. Okay. X equal 3 and x equal 3. Well, those are the same numbers, but that's a multiplicity of 2. So that's what they mean, multiplicity of 2. So that is 2 zeros, but they're the same numbers. Okay, so you have to count that in here. Okay, now let's see how they did it. That factored as x minus 3 times x minus 3 has exactly 2 zeros, x equal 3 and x equal 3. It reminds you of the old Bob Newhart show. This is my brother Daryl, my other brother Daryl. Okay, they're the same name, but this is the same number. In fact, this is called a repeated 0, but it counts twice because there were 2 factors. Okay. See, is there a C? Okay, here's a third degree polynomial function. How many zeros you think it has? Complex zeros, 3. It's got to have 3. Well, first thing you do is factor whatever you can. Well, I know I can factor out an x, and that gives me an x squared plus 4. Okay, now 1 0 is going to be x equals 0. Okay, but then if you set this equal to 0, x squared plus 4 equals 0, there's no real number that's going to be true for. So you have to go to the complex numbers, subtract 4 from both sides, and that gives you x squared is equal to minus 4. So x is going to be plus or minus the square root of negative 4. Well, just like we did before, that's plus or minus the square root of minus 1 times the square root of 4. Well, the square root of minus 1 is I, but let's start with the 4. Square root of 4 is 2, and square root of negative 1 is I. So plus or minus 2i. 2, right. So here's 1 0. Here's the next 2 0. In other words, x equal 2i and x equal minus 2i. That's 1, 2, 3 zeros. And sure enough, that gives you your 3 complex zeros. 1 is real, 2 are complex. These 2 complex zeros, I'm just going to point out to you now, happen to be complex conjugates of each other. Okay? The a in both cases is 0, 0 plus 2i, 0 minus 2i. Those are complex conjugates of each other. So let me erase my scratch here so you can see what the book does. And it factors it just like we did. And then it factors that to be x minus 2i times x plus 2i. So they're doing the factors. And here are the zeros. X equal 0, x equal 2i, and x equal minus 2i. So yeah, they came up with the zeros of that third degree polynomial function. Has to have 3 zeros in the complex number system. Okay. Now, I don't think there's a D part, is there? No. So that was example 1. Example 1 is followed by a checkpoint. Please do the checkpoints. All right. Now, what I was just telling you, I didn't realize was here on the next page, page 153. There is the French mathematician Jean-Laurent D'Alembert, who actually came along before Gauss. He lived a whole lot longer. No, I'm sorry. I'm sorry. I was looking at the wrong dates. He worked independently of Carl Friedrich Gauss in trying to prove the fundamental theorem of algebra. His efforts were such that in France the fundamental theorem of algebra was known as D'Alembert's theorem. But he came ahead of him, but evidently Gauss beat him to it as a young man because they overlapped very little. Gauss was born in 1777 and D'Alembert died in 1783. Gauss was only 6 years old. So evidently D'Alembert did not fully prove it. Gauss did. Maybe he used D'Alembert's work, and because of that, the French like to call it D'Alembert's theorem. Okay, so let's go on to the rational zeros test. Now, this is one of the most useful tests you'll run into. Okay, it helps you find those zeros. Okay, the rational zero test relates the possible rational zeros of a polynomial, only possible. Now, these polynomials have to have integral coefficients. You can't have fractional coefficients. You can't have decimal coefficients. You can't have radical coefficients. You have to have, and you certainly can't have complex, as in imaginary parts on your coefficients. So these are integer coefficients to the leading coefficient and the constant term of that polynomial. So here's what it is. This polynomial function, f of x, a sub n, that just means this is the coefficient that goes with x raised to the nth power. This n is crucial to the problem. This n just says this is the coefficient that goes with that value of x, okay? Plus a sub n minus 1 times x to the n minus 1, and you keep on counting down until you get down to a sub 3 x cubed plus a sub 2 x squared plus a sub 1 x plus a sub 0. Now, as long as all those a's, every one of those a's is an integer, integral coefficients, they can be plus or minus. Remember, integers can be plus or minus, but they can't be fractions, decimals, or irrational or something like that, and no i's in them. Okay, then every rational zero, now the rational zeros can be rational. The coefficients have to be integers, but the zeros can be rational, of that function f has the form of p over q. Okay, what in the world is p over q? P and q must have no common factors. If they do, factor them out. Okay, now any common factors other than 1. Okay, and p is a factor of the constant at the end of the problem, a sub 0, and q is a factor of the leading coefficient, a sub n. Okay, that's all you need. You don't use any of the ones in between, just the one at the end in the numerator, the one at the beginning in the denominator. And these are factors of those numbers with no common factors. To use the rational zero test, you should first list all the rational numbers whose numerators are factors of the constant term and whose denominators are factors of the leading coefficient. So the listing of all possible rational terms, factors of the common term divided by factors of the leading coefficient. Having formed this list of possible rational zeros, use trial and error to determine which, if any, are actual zeros of the polynomial. We'll show you how to do that. Note that when the leading coefficient is 1, then the factor of the denominator is plus or minus 1. Hey, they're all going to be integral things, no ratios involved. The possible rational zeros are simply factors, integral factors of the constant term. Okay, so here we go. We got time, yeah. Find the rational zeros of this polynomial function. F of x is equal to x to the fourth minus x cubed plus x squared minus 3x minus 6. Okay, well, all the rational zeros will be of the form of p over q, where p is all the possible factors of 6 over all the possible factors of 1. Okay, well, what would that be? Plus or minus 1, 1 will go into 6, plus or minus 2, 2 will go into 6, plus or minus 3, 3 goes into 6, 4 won't go in, 5 won't go in, but certainly 6 will be. So plus or minus 6 divided by, all you got there is plus or minus 1. Okay, so guess what? These are your rational zeros. Plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. All right, now let me show you the very easiest one to check, because it's always going to be there, plus 1. Okay, what you do for plus 1? These are the zeros, so you let x equal 1. Okay, so that's your first guess, x equal 1. Well, if x is equal to 1, this is 1, this is minus 1, this is plus 1, this is minus 3, and this is minus 6. Well, this adds up to minus 10 plus 2, that's minus 8. That is not equal to 0. Okay, so you rule out the plus 1. That's out of there. Okay, you still got minus 1 to go. The easiest way to check now, for x equal 1, just add the coefficients. Okay, that's all. Okay, all the rest of them, rather than plugging in, use synthetic division. So we'll do minus 1 into, and then do our synthetic division. Inside the house would be a 1, minus 1, 1, minus 3, minus 6. Now, I always stop and count. 1, 2, 3, 4, 5. One more than the maximum exponent, I've got them all covered. Skip a line, draw a line. I'll never see that in the book. Bring down the 1, and then multiply and add. Minus 1 times 1 is minus 1. This adds to minus 2. Minus 1 times minus 2 is 2. That adds to 3. Minus 1 times 3 is minus 3. That adds to minus 6. Minus 1 times minus 6 is plus 6, and ding, 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 we have a 0. So x equal, where's my thing? X equal negative 1. There's a 0. Okay? Now, where do we go from there? Let's try 2. I like positive numbers better, so let's try 2, and let's see if 2 will work. Again, skip a line, draw a line. You can use the quotient now. So that'd be 1, and this is 2. That adds to 0. This will be a 0. That will be a 3. This will be a 6, and ding, 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 we have another 0. X equal 2. Now guess what? You're down to 3 terms. This stands for x squared plus 3 equals 0. And guess what? The only way that can happen is if you have complex numbers. So these are your 2 real zeros. These will be 2 complex zeros. You have a total of 4 zeros. You found them all. Now, I'm not going to mess with these, but this would be plus or minus root 3i. Okay? Which I like to write as x equal I root 3 and x equal minus I root 3. Now, that gives you your other 2. I'm not messing with the complex ones with imaginary parts to them. Okay. So, we found them all. 1, 2, 3, and 4. Basically, I'll be asking you to find all the real zeros because you don't have to do, oh wait, I'm in the wrong thing. Let me erase this and we'll see how they did it. How we doing on time? Yeah, we're okay. Okay. Because the leading zero is 1, the possible rational zeros are only the factors of the constant term, which is plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Okay? Now, they just started with the 2 that work. Okay? We started with the first one. It didn't work. Okay? It's trial and error. Okay? But for, I guess, time's sake, they started with this one. They found out that was a 0. Then they went to 2, which we found out was a 0. But once you get to this stage, and that's why I like to do this, separate those off. Those are your remainders. These are your quotients. Okay? And then on this quotient, you know that stands for x squared plus 3. Once you get to that stage, and this, by the way, is the factorization. If that's the 0, x equal minus 1 is a 0, x plus 1 is a factor. And if x equal 2 is a 0, x minus 2, get out of there, is a factor. And then we know that's a factor. So this is another thing you can do. This is how you factor polynomials, getting all the factors that the linear factors out of it and what they call irreducible quadratic factors in the complex, in the real number system. You cannot factor x squared plus 3 in the real number system. You can in the complex number system, but not in the real number system, because that's called an irreducible factor in the real number system, or under the reals they'll call it. Okay. Because the factor x squared plus 3 produces no real zeros, you can conclude that x equal minus 1, x equal 2 are the only real zeros of f, which is verified here. If you had plotted that thing, you see it intersects the x-axis at x equal minus 1 and x equal 2. Okay, it's not a parabola. It sort of looks like one, but you see it has more of a curvature here, more straight here. So that's not a parabola. Don't call it one, but it sort of has that appearance. Up here, it's looking a lot more like a parabola, but don't be fooled. Okay. Only has one turning point rather than 3. Okay. Now, when the leading coefficient of a polynomial is not equal to 1, then your list of possible rational zeros can increase dramatically, and it increases with a bunch of fractions as well, which are not particularly fun, but they're doable. In such cases, the search can be shortened in several ways. A programmable calculator can be used to speed up the calculations. A graph drawn either by hand or with a graphing utility can give you a good estimate of the location of the zeros, and the intermediate value theorem, along with a table generated by a graphing utility, can give approximations of zero. Okay, we can do it all by hand usually. Okay, and synthetic division can be used to test the possible rational zeros. That's what I use. Okay. Finding the first zero is often the most difficult part. After that, the search is simplified by working with the lower degree polynomial quotient once you found an actual zero, and using synthetic division. And we did that in the last example too. Recall that x equal a. If x equal a is a zero, then x equal a is a solution to the polynomial equation f of x equals 0. That's what it means. It's a solution when the y is equal to 0. All right. Oops, we've just run out of time. Okay. I'm trying to see where we left off. I'm sorry, I didn't realize that we skipped example 2. So we're going to do example 2 next time, and we will skip example 3. Already done. Okay, sorry about that. Okay, so we will start with example 2 next time. Sorry about that. I didn't realize they skipped example 2. Now, let's see. Do we have any homework exercises you can do in this section? I think you can do 9 through 13. Odds 9 through 13. They're all at Calc Chat. 9's at Calc View. And I think you can do 15 and 17. You may be able to do 19 through 27. 15 and 17 are both at Calc Chat. 19 through 27 are all at Calc Chat, but 25 is at Calc View. Okay, and we'll pick up the rest of those next time. All right, there were some questions to be asked. Did you need this to be private, or can you ask it in front of everybody else? I think it was Shay, wasn't it? Shay, are you still there? Hello, Shay. Yeah. Okay, do you want to ask it in front of everybody, or the few people that remain, or you want to wait till they leave? Okay, folks, can y'all get out of here? Okay. Unless someone else has a question you don't mind asking in front of others.
And we are on 2.4, right?
No, we just got into 2.5. We finished 2.4 today and started in 2.5. We're on page 153 in 2.5. Okay. Say that again. Where or when? Where? Okay. When is anytime you can, as soon as you can. Where? Okay, and this is a great question. You can send it to me on an email, as an attachment to an email. You can send it to me as an attachment to a Blackboard message. Or if there's a place in Blackboard under whatever week I passed it out to you that says test 2. So find the week when I passed it out to you, and that's why this isn't a great option, because you have to go looking for it, and Blackboard is so awkward to deal with. But if you know which week I gave it to you, go to that week. When you see test 2 or whichever test you're talking about, then you can submit it that way. To me, that's the harder way, but you can either attach it to an email or to a Blackboard message. Did that answer your question? Surely. You too. Thank you so much. Okay, the rest of you, can y'all go on and get out so Shay can ask her question? It may be, Shay, that they are not even near their phone, computers anymore. I don't know. Sometimes I think people just turn on their box and leave and do other things. So it's up to you. You want to give it a shot? Okay. Well, do you want me to end this one and start another one? Let's see how to do that. I don't know. That would take too long. Can the rest of you get out, please? Okay. Would you rather I give you a call? Well, one person left. Okay, another left. We only got 3 left. Could y'all sign out, please, so Shay can ask her question? Tanisha, Anaya, and Dee. Class is over, but okay, we lost one more. Only Kanisha and Anaya. Can y'all please leave? I wonder if they even can hear me. Okay. Kanisha and Anaya, can you go? Well, you want to risk it? Shay?
Sorry.
Do you want to risk it? These two don't seem to be anywhere close.
I'm not gonna worry about it. I ain't gonna worry about it.
Do you want to ask the question? You can email it to me.
I tried emailing, it didn't send. I'm just not gonna worry about it.
Okay. Are you sure? You sure that it's? I mean, it sounds like it's important enough you asked to do this. I would say, do you want me to give you a phone call? But that would be putting your number out here. I guess you could send me a chat with just your phone number on it, but only send it to me and not anybody else.
I'll try to email it again.
Okay. Okay, now I'm in class basically all day today, so I may not see it till the end of the day. But if I do get a chance, well, in the middle, from 1 to 3, I'll be checking emails, so I may see it then. Okay?
Okay.
All right. Sorry about that. Okay, well, I'll go on and end the meeting for everybody. So take care. We'll see you on Thursday. Okay? All right. Bye-bye.